So, good afternoon, everybody. You can hear me okay? So I'm fairly recently appointed as the project scientist for user support at STScI for JWST. I've been involved a lot with the JDocs development. I've been involved a lot with APT development, and also part of the effort to bring you these separate target visibility tools. Today I'm mostly going to talk about one of the tools, and I'll talk about the one that deals more with coronography tomorrow afternoon when we talk about coronography. I'll mention it today as we go along. So the APT tool, of course, is the real scheduling, checks the schedulability of your observations, and by that I mean it does not just visibility of your targets, but it looks at whether or not you have guide stars as a function of time. If you have, within APT, actually specified special requirements on your observations, it takes that into account to judge the schedulability. But it's a fair bit of effort if you just want to understand for a quick look for a target what the visibility looks like. You have to get into APT, you have to enter a target information, you have to enter a provisional observation, and then run the part of APT that's called the visit planner. You'll hear about this tomorrow. And at that point, you either get a green check that says it's schedulable or a red X that says it's not. And at that point, you can then open up some diagnostic plots that tell you some things about the general visibility of your target. That's a lot of work to go to for an individual target. Also, if you had a bunch of targets you wanted to do this for, where it mattered what the visibility was or the position angle in the sky was as a function of time, it's fairly difficult to do that within the APT environment itself. So if you just want a quick overview, APT is kind of not the right tool, and we've come up with a couple of other tools that should allow you to assess that visibility. So the target visibility tools are really just a quick look tool. They're not looking at guide stars. They're not looking at any special requirements that you may end up putting on your observation. But in reality, they may be helping you figure out whether you need to put special requirements on your observations when you get into APT in order to do exactly what your observation, your science case may need. So for a given target that you enter into one of these tools, it will calculate the visibility windows over a specified period of time, has a default period of time, or you can specify a range. And it also then gives you position angle versus time, either for a particular instrument or more generally for all the instruments. Now, if your observations don't really depend, are not time dependent, or if you don't care about the position angle on the sky, well, maybe you don't even have to run these tools. But there are many use cases where you might want to adjust one or the other of those parameters, if not both of them. They're related, obviously. The position angle in the sky changes with time. And so I would actually like to take a little time this afternoon, as well as showing you the general tool in a little bit of detail, to also just give you a little bit of background for why these visibilities and position angles are changing and why it's restricted for some targets and not so much for others. And in particular, one of the things that we're not generally used to thinking about is the ecliptic coordinates of your target as opposed to the regular RAN DEC or even galactic coordinates, but it's the ecliptic coordinates that actually matter to JWST visibility, and I'll show you a little bit about that and why. Okay? So where might this be useful? Well, let's say you've got a supernova program, and a supernova, you've been accepted, and the target of opportunity trigger goes off, or you have a supernova. You want to check out, first of all, is it visible to JWST at all right now? And second of all, maybe I want to monitor that since it's a phenomenon that's changing with time. So how long can I see it before JWST loses visibility on a target like that? That would be one case. Timing possibilities, anything that requires a specific time of year to be observed. As you'll see as we go through a few more slides, the JWST field of regard moves around the celestial sphere, and so there are times, depending again on the ecliptic latitude of your target, when you can't observe, possibly, with JWST on a particular target. For mosaic planning or coordinated parallels, let's say you want MIRI and NIRCam imaging, and maybe you want to image a piece of the sky, you mosaic a piece of the sky, and you do this trick that they do with Hubble where you come back roughly 6 months later, and the fields of view have switched around so that you can then do the other patch of sky with the other instrument, that kind of thing. Do you have visibility 6 months apart that you can do that, or the angle's right and so forth? You can check out that kind of thing in an overview kind of a mode and see how much flexibility you have for the planning. And then many applications within coronography. The coronagraphs, many of them have structure in the field of view that you need to avoid. If you have a disk system, you don't want to put the disk right along the occulting bar. You want to make sure that you're off that, for instance, or maybe you've got an exoplanet system with known planets, and you don't want your known planet to end up on one of those structures in the field of view. When can I observe? Actually, APT does not give you that level of detailed information. The coronography tool that we'll talk about tomorrow actually gets down to that level of detail for you. So hopefully there's real value added to these tools. Now here's a plot that gives you a little sense for what's going on. There's kind of different ways of looking at these things. This is a plot now of how many days per year you can observe a particular spot on the sky versus the ecliptic latitude along the x-axis. And you see this rather bowl-shaped shape that comes up to about 45 degrees and then takes on a different shape above plus and minus 45 degrees. Down in this zone here, you'll have two observing periods separated by about 6 months on your target. And from the 100-day minimum on this graph, you have at least 50 days in each of those two windows, or possibly more, as you go out toward 45 degrees. And then as you get above 45 degrees, all of a sudden you will see in the visibility plots that you've got one longer window of visibility for your target, and then a long period where you cannot access the target. So your visibility depends a lot on the ecliptic latitude. The other part of this, though, is that the position angles, if you have position angle constraints, for instance, for some of the coronography observations, just as an example, the angles that you can actually obtain at any time are restricted down here at low ecliptic latitudes, and you may have situations that are just simply not observable to JWST if you're down at low enough ecliptic latitudes. Whereas at higher latitudes, you have a lot more visibility, you have a lot more flexibility of available position angles, if that matters to you. Although, for instance, if you're doing a very large mosaic, the amount of time you can get at one position angle on the sky is still restricted to about 10 days maximum. So you could actually ask for a large enough mosaic that it can't be scheduled at the same angle because of that restriction. So there's another way of looking at that, and this is another kind of takes a little bit of explanation to understand this. So now I've got ecliptic latitude on the y-axis, okay, and the V3 position angle is the reference position angle of the observatory as opposed to one of the instruments. You could also make a plot like this for each of the instruments. Several of the instruments are pretty closely aligned to V3, and a couple of them are offset. MIRI is offset by about 5 degrees, and NIRSpec is actually offset by quite a large amount. But anyway, just as a reference point here, the colored region is the area that at any particular time JWST could observe. And you can see, again, what happens as you get above about 45 degrees is all of a sudden you've got one longer period all the way across in position angle here that you can observe, whereas at these lower ecliptic latitudes there are two periods separated by about 6 months. The color coding here is the length of time you can stay at a given position angle. So most of the sky you can only stay at a given position angle about 10 days, if that matters to you. And the good news at low ecliptic latitude is if it's an allowed angle for you, you can stay there for a long time, up to 40 or 50 days at the same position angle, but you only get basically one position angle plus or minus 180 degrees. So again, you're restricted in angle, but you can stay there for a long time. So these are the kinds of considerations that come into not only planning JW observations, but from your perspective, it can possibly affect your science cases as well. So here's a little picture, a little graphic of JWST. The sun is coming in from the right here, and you can see that there's this range from 85 degrees solar elongation to about 135, where JWST can point and observe. and then you can take that and rotate it all the way around 360 degrees in the other direction. As long as you keep the sunshade here toward the sun direction, you're good to go. So there's a big annulus on the sky, but you have to stay within 85 to 135 degrees. Okay, and here's this V3 reference axis of the observatory. Now, if we take that and project it onto the celestial sphere, it looks more like this. And this is what is called the field of regard, the region of sky that JWST can observe at any particular time. Again, the sun is coming from the right. There's our angles again, and this shaded annulus here. Anywhere in that annulus, again, 360 around the celestial sphere, is where JW can observe at any particular time. So at any given time, you can get about 40% of the sky that's available. And then, of course, that whole pattern moves about a degree a day as you go around the sun, and you eventually sweep out the entire sky. So maybe you can understand where if you're down here on the ecliptic plane, you make one pass through the annulus, and you wait for the other side of the annulus to come around, and you get another pass through the annulus. There's your two observing windows that you've got for a low ecliptic latitude object, whereas something up here at higher latitudes, you can imagine a longer period as that annulus sweeps. You're not actually getting cut by the anti-sun region here, and so you have one longer period north and south instead of the two visibility periods that you get for lower latitudes. So there's a little insight into what's going on and why it's a little bit tricky to estimate visibility just kind of from first principles. You kind of have to take all these things into account. Another thing that's important for some applications is the ability of the observatory to roll off-nominal roll around the V1 axis, which is the bore sight of the telescope. So it's coming right out of the screen toward you in this particular orientation. And it can only go about 5 degrees plus or minus from a nominal roll to stay behind the sun shield. So that is basically at a degree a day, that's 10 days. Roughly plus or minus 5 degrees is your 10-day visibility window at a given angle. You can go off nominal plus and minus a little bit and stay at that angle for about a 10-day period, and then you got to change the angle. Okay. Now, a little detail that's more important for coronography than anything else, this plus and minus 5 that I show on here is actually varies from plus and minus about 3.5 at the 85 degrees side of the sun exclusion to about plus and minus 7 degrees over on the 135 degree area. And so for coronography, if it matters to you to get a little more roll angle, it restricts your visibility when you try to plan it. Okay? Okay, so we've constructed two tools for you. One is called the General Target Visibility Tool. That's the one I'll talk about in a little more detail coming up. It's just a command line tool, and once you run the command line command, it pops up a GUI that you can interact with if you want to, or you can send the outputs to files instead of coming to the screen and so forth. So we'll go through some of those options for you. They're really quite straightforward. This gives you the angles for everything. As a matter of fact, it gives you the plus and minus angles for each of the instruments, each of the 4 science instruments, for the FGS, if it matters to you, for the guidance system, and also for that reference V3 axis. And you'll see, if you look carefully at the numbers, that the V3 axis and, for instance, the NIRCam axis are very, very closely aligned. But it gives you the whole ball of wax in one go. You get plots for all of them. You can restrict it to one field if you want to, but it gives you plots for everything, and it gives you the numbers for everything by default. And then there's a second tool, that's the coronography tool, that I'll talk about in more detail tomorrow. That is a GUI-based tool that you literally just type the command to start the GUI, and everything else is done from within the GUI in that particular example. And again, the coronagraphs have structures you may want to avoid, and APT, even if you went to the trouble to go into APT and go through all that to see the diagnostic plots, they don't get down to the individual field of view level that you'll get out of that tool. So that can be quite useful to you. Okay, so some of you were struggling with getting this to go. This is the harder part of running the tools, getting Astroconda up and running. Hopefully, most of you got that straightened out, although I understand that we've got an issue with PC users, so we'll have to go back and talk to our IT folks about that. And we didn't, honestly, I was not aware of that project. We haven't gotten any calls into the help desk from PC users about the target visibility tools, which is I'm a little surprised. But if this is a generic problem, we need to obviously track that down and get that working for you all. Astroconda is not my specialty, but basically this is the way the Institute is going to distribute software in the future. And so it's kind of a hassle to get this installed just for these target visibility tools, which are one command lines that you run on the command line. But as these tools are updated, as other tools are updated, they will be distributed through this Astroconda. So it's really not a waste of your time to go through the hassle of getting that all installed. Just a little exercise we went through earlier today. If you had time to actually look at the JDocs pages for this, I think they're pretty adequate. They point you to the right place, and if you actually follow the steps in the, not only in the JDocs article, but in the articles that they refer you to for Astroconda download, it looked like they actually worked with, for Mac users anyway. So if there are problems with that, we need to know about it. But I think once you get it installed, then running the tools is very straightforward. Okay, so let me talk a little bit specifically about the general tool now. It is Python-based, but it kind of doesn't matter to you all. You don't have to know Python. It's literally just the tool name, and you enter a right ascension and a declination. You can do that in decimal degrees or in the sexagesimal format, so either of those will work in the tool. And then there are a bunch of flags you can add onto that if you want to do specific things, and we'll talk through some of those options. The defaults, if you just did that, tool name, RA and DEC values, the default is that you get an ASCII table that is dumped to the screen, which is not terribly useful because it goes on for, if you did it for a year, you get one line per day, so you get a 365-line file getting dumped to your screen, but that's what it does. You can put that to a file if you want to. And then you get a plot, a GUI plot that you can interact with that pops up on the screen. That's your default for this tool. But when I say interact with the screen, you get 6 little plots, one for each of the 4 science instruments, one for the V3 axis and one for the FGS. If you want to, you can just run it that way and then use the tools in the GUI to grab one and enlarge it up to look at it in more detail, or even look at part of a plot in more detail if you want to. One of the command line changes you can make is to specify which instrument you want the plot to come up for, and just get one instrument. So again, this is there's a lot of flexibility with the command line options that you can add on to this tool. The other thing that you might find interesting is that this tool can be used for batch processing. And basically all you do is you take a sequence of the commands that you want to run and put them in a file, make the file executable with chmod, blah, blah, blah. Make it an executable file and type the name of the file, and it will run the tool for each of the lines that you've put into the batch file. So if you had a bunch of targets that you want to just get an overview for, I would recommend that you make your little command so that it sends each of the files to a different plot file name and to a different text file name, so that you have all those outputs out there rather than having all this stuff spew up to your screen, obviously. But there is this batch processing mode which you might find useful if you have a bunch of targets that you would like to run. You can use a Python script or whatever you want to construct the little control file that allows you to do that. Okay, so this is just an example of one of the plots that comes up then. If you run this in a very simple mode, in this particular case, I just ran the tool name, put in the R and DEC, and I actually used a flag here to at least get a name on the plot, so that if I saw that plot later, I remember which target that was for. By default, you don't get anything but the RA and DEC up here, but if you add a target name with that flag, you'll get the name on your plots there. And again, you get a plot here, then here's the V3 axis, near cam, MIRI, and so forth for all 6 of those fields. If you were in the active GUI at this point, you could come in and just grab one plot and blow it up and look at it. Or, again, there's a flag you could put on here to say, I just want to see the near cam plot on my screen from default. You could also change the time range. This is the default time range, which now starts way back in 2018, which I guess doesn't matter anymore. Maybe we can tweak that up in a future release. This is just the top part of the text file. that comes out. In particular, I just wanted to highlight that even though it spews out maybe 365 lines if you've done a whole year or something like that, it's at the top of the file where it actually tells you what your ecliptic latitude of your target is. Of course, it gives you the area deck back and whatnot for reference. At the top part here are the overall summaries of the windows that are available. So I actually ran this in default mode, and so there were actually 3 visibility periods within the time period of interest here. So it tells you the start and end date of each of those, the duration of it, so 200-day window for this target because it's above 45 degrees. And then start and end, RA deck, whatever, and start and end time, sorry, and then here's your RA deck, just repeated out here. And then for each day, it goes through, and for each of the 6 options, it gives you the minimum and maximum. So you'll see that change from this roughly plus and minus 3.5 number to plus and minus 7-ish as you scroll through an entire year, or as the visibility goes through the annulus, for instance, in each target's case. Okay, and so that file goes on forever. It's a long ASCII file that gets dumped out. So if you wanted to, you could actually come in here and plot this stuff yourself or whatever. You get an ASCII output file for each of these runs. So here's one of the panels just blown up larger so you can see it a little bit more. So we're seeing the available position angle as a function of time, and you can see the pattern just repeats here pretty much from year to year since this is a default time period that was run. Obviously, it's a little hard to read that, but you can see that you get quite a large range of potential angles on this target from 250 down to about 50 degrees on the sky. These are standard astronomical position angles of the reference axis east of north. All right, so 50 on that scale is 50 degrees east of north for the observatory V3 axis in that particular example. Okay? So I'll look at a few more examples with you in a minute and show you what some of the flags are and whatnot. They're all there in JDocs in the reference articles for this. I did want to mention that as you saw this morning, the backgrounds do vary not only with wavelength but with time, especially for the Zodi fraction of the background. Well, I mean, the instrumental thermal background is going to change somewhat with time as well. And so if your science use case is an example of where you're in a background limited situation where you want to minimize the background, you will need to restrict the visibility from what the visibility tool tells you. It just calculates the overall visibility window. It's not looking at the background. We expect to actually have a tool, if not exactly like this, similar to this, available. Jane Rigby down at NASA Goddard had constructed a prototype tool that we're trying to get released that would allow you to assess the situation yourself if you really needed low background. So just as an example, here on the right-hand side, we're looking at 4.5 microns. This particular target, the full visibility window here, which is the entire bowl shape, you can see it just wraps around for the year here. That entire visibility window is what the target visibility tool is giving you. If you wanted to restrict yourself to maybe just 10% above the minimum background you could get, you would have a much more restrictive visibility window in the middle of that range. So if you're particularly interested in backgrounds, hopefully we'll get this tool online that would allow you to assess how much you'd need to take the output from the target visibility tool and maybe shrink that in a little bit to make sure that you have the low background that is needed. Okay, so that's still TBD. That's hopefully coming along. Okay, so there is help in JDocs. Maybe some of you have seen that article already as we were getting ready for this. There obviously is still, we haven't said much about the help desk today, but instead of an email help system like was available for Hubble for a lot of its lifetime, there is an actual system that you can interact with that uses that MyST account that you log into. You can ask questions. You can actually see what other people have asked. There are, as we see, a number of questions coming in about a topic. We may actually write up a little article called a knowledge base article that is in the help desk area that you may get directed to as you start to type your question. It may actually give you a clue that somebody else has asked this question and there's already an answer out there for you. There are links that actually point to JDocs from knowledge base articles if it's relevant. We're trying to capture the kinds of questions that people are asking if they're not in JDocs so that we can actually enhance JDocs and try to include that in a future version of JDocs itself. It's going to be a very useful functionality, I think, for the user community to use the help desk. So please consider going to that link and checking that out. And so I'll try to do a little demo here. I was just trying to get my computer set up before the talk. I think I can at least show you what some of the commands look like for various options, and we can even try to bring it up if you'd like to. And then we'll have the hands-on experience after we take a little break. So does anybody have any questions right now before I try to do the demo? Anybody? And I apologize, this is going to be pretty small, but let me just first of all just highlight in JDocs. I think this one I should be able to make bigger. Okay, let's do that. Maybe you can see this. I thought I had the, yeah. So that one's small too. Let's get it up a little bit bigger. Okay, so let me just point to the side here for a moment. So under Target Visibility Tools, there's a top-level page that discusses both of the tools, and then there are two articles, one for each of the tools. That's basically a help file, how to install, how to run, and some examples, okay? And so right now I happen to have the general Target Visibility Tool article up here so you can see it. I just want to look at the main headings in here after some initial description. Gives you some background here for the position angle stuff that I talked about a little bit, and the coordinate system and field of regard stuff, so you can review that if you want to. And then it goes into how you install this and how you run the tool. And again, it takes a little bit of patience to look through these articles a little bit, but between the JDocs article itself and the references that it provides, for instance, going to here's installing Astroconda and so forth, those links take you to help files that tell you exactly what you need to do to get Conda and then Astroconda loaded onto your machine so that these tools will run. And then you just open up a terminal window, which I've done over here. I happen to have an X terminal window open or a regular terminal window. And you say source, activate Astroconda to open up the Astroconda environment on your machine, which I think I have already done over here. Yes, it says Astroconda right there. And then it's just a matter of typing the tool name, JWST_GTVT, and giving it a right ascension and a declination, and it would literally run just from that much information. And then there are the flags that you can add to it. So here's a section on this page as well that gives you a lot of what these flags are and the usage tips. Just to highlight a couple of them, just to give you a sense. I mean, the format is all the same for these things. If you want to save it to a plot, there's the command that does that, --save_plot, and you give it a plot name. Same thing for the table, so you can send those out to tables. That's the kind of thing you would do in batch mode rather than have it spit to the screen. If you wanted to have individual instrument, and again, there are examples on the page that show you exact formats. It's just lowercase, nearcam, MIRI, whatever, for the instrument, specific instrument. If you want to have a name on your plot, and so forth. You can see there's start date and end date. This is probably as useful as the actual demo will be, because you just add these flags, and again, there'll be examples down below this in that same page that show you the format for the dates and so forth and so on. So there's examples out on this page, so it's almost one-stop shopping for this tool if you can get to this page in JDocs. Okay. Now, since I am such a slow and terrible typist, what I have done, that's not what I wanted. I thought I had it open. Here it is. Okay. So I could run it the simple way, but I thought I would start with this example that's highlighted on the screen right now There's the tool name, RANDEC, minus name, STScI, the instrument, near cam only, so it's just going to bring up one plot so we can actually see it a little bit. And I'm actually going to send the output to a table or to an ASCII file instead of having it come up on the screen. So I'm just going to come over here, and I'm in an X window. How do I get this to... Oh, phooey. I don't have my mouse. I need a center click. Do you remember what center click is on Mac? With just the... Anybody know what center click on the Mac is?
Option.
Option?
Option click.
Thank you. Nope.
Go to Exports Preferences.
No, I'm not going to do that. I'll tell you what. Let's get up a regular terminal window instead of an X window. Oh, that's really useful. Okay, now I got to get over to...
Source activate asterisk.
Yeah. I have to get to the right directory where my file is. I'll tell you what, maybe it's going to be easier to bring the file out onto the desktop. Let me do that. I'm sorry. I had this all set up before we moved the computer up here, and a bunch of stuff went away, so I... let me...
It takes 2 seconds to do the Exports Preferences. And you can just middle click copy.
Where is it under?
Exports Preferences. Go to Pasteboard.
Go to what? Pasteboard.
Then update pasteboard immediately when text is selected. The bottom one checked. And go to output. Input rather.
Emulate through.
Yep.
Am I going to have to open up this X window again to make it work?
No. Should have.
Ah. Let's just try the simple case and see if we can
Do
get
a
it.
Command C to copy it.
Yeah.
No pressure.
All right. I just want to show you what the output looks like here, so I'll do it the old-fashioned way here. 325.678 and 43.5. So this is the simple mode. There's the big ASCII file, and there is the plot. Okay. So that resizes. So there are controls down here on the plot. One is zoom and rectangle, and so this is a click to activate it, and then you can come up and pick a particular, sure you can. All right, it's not, I should have brought my mouse up. I'm sorry, this doesn't seem to want to cooperate. Well, to get out of it, you just click out of the plot, and that closes it. Let me go back to the top of the ASCII file, and you can see that example that I showed before with the windows and the ecliptic latitude is shown at the top of the file, and then there's the long ASCII file. I'm going to try something here that might help you out a little bit. Oh, thank you. I wonder if that'll help me or not. So let's just try that a second time and see if it lets me play with the plot. If I could see the mouse, I'd be, oh, I better. Okay, so here's the zoom. Just to show you, this is a, you can reset to this original plot with that home. Lets you scroll forward and backward through the different plots that you've made, if you've made a bunch of them. You can pan axes, and then this is the zoom. So let me see if this is going to work this time. It's not. Interesting.
You have to click and drag instead of.
Yeah, I'm trying to click and drag, and it's not. Well, come by and see me later because it works on not this way. All right, let's try since I think we can. All right, I want to go back to my desktop. Are we out of time yet? Okay, thanks. All right, I'm going to try another one. See if that shows me a plot for one instrument. Okay, so there it gave me the plot for one instrument. I still haven't restricted the time frame. Right, just for grins, let me see if it works if I try to zoom in. Ah, it's decided to let me zoom in on this one. So somehow coming out of an X window instead of a regular terminal window, it was not happy. So I'll make note of that, although I've used X windows before. But again, you can actually zoom into even a subregion if you want to. Again, these plots let you go back or forward through your plot stack. One thing of interest that you should note is that you click to get into that zoom mode, and then you have to click it again to get out of it, okay? Which for the cornographic tool, you may want to be able to access that. And you also saw that it didn't spew the ASCII to the screen that time. It's because I told it to send that to a file, so that didn't come up, okay? Let's look at another example that you'll actually look at in your exam, not the same one exactly, but here is a low ecliptic latitude, and you'll see how it changes the appearance. Of the visibility plots. I'll come here, see if I can zoom one up. Ah, you have to be in the plot area for it to zoom. That's what's going on. So if you want to examine that one in more detail, you can blow it up. Interestingly enough, in that particular example, now that I've blown it up, you're seeing the effect. The width of these lines is the plus and minus angle that's available as a function of time. And so you can see how it actually changes from one end of the visibility window to the other, where it gets a little wider. And that's that going across the annulus example, okay? Hopefully that's enough to get you started in your examples. I'm sorry that was a little bit ragged. Like I said, when I moved the machine up here, some things went away that I had set up, so I apologize for that. Any quick questions before we break? Or come up and find me afterwards. How long is the break?
30 minutes.
30-minute break, and we'll come back and try the tools out, okay?
So are the commands available for your command example?
It is. Does everybody have access to the ESAC site, Marco or Maka? Are they around? I actually uploaded it to, or I gave it to Maka. She put it on the ESAC site. I don't know if does everybody have access to the presentations and stuff?
By the way, I see most of the commands you're just using the web page of the
The examples are right in, a lot of those examples or similar ones are in that JWST page, so maybe that's a good place to go to. General Target Visibility Tool page and the examples section at the bottom of that page. Okay, thank you all very much.